Okay, welcome back. We've just covered a lot of information, and we're going to finish off just by talking about macroevolution. So macro's big. We've talked already about microevolution, these small changes in allele frequencies. What about big jumps, right? So they're both evolution, and macro is made up of micro, like lots of little changes could equal a big change, right? Um, but macroevolution refers to these big changes over time that results in like speciation, not just the population turned a little greener, right? Or a little oranger or a little bigger, right? This is big changes, new species. They're both made up of the same thing. Macroevolution is still a change in allele frequencies, right? It's just bigger and more visible. So, this idea is of punctuated equilibrium is that evolution doesn't always occur in this very, very steady rate, right? So if we're, if I were really good at drawing, if we went from like a circle to like thousand-sided thing, oh wait, I'm sorry, um, lots of sides to maybe like something like that, and then we get and then maybe eventually like a square, right? Okay, so this would be a very, very slow evolution over time. That maybe we'd see in the fossil record, these little changes, right? But sometimes you don't see that. What you see instead maybe is a circle and then that and then that, right? Big changes in your fossils. And maybe it happened over a short time. Maybe there was a burst. Maybe everything was circle, circle, circle all along. And then hexagon, 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 and then square, right? So these are like when there's no missing link. So maybe there was a real rapid change in the morphology of organisms, really rapid evolution. So this is like if the environment and everything else stays the same, maybe there aren't selection pressures. And then maybe something happens like a meteor, right? And suddenly everything changes and you're going to start to see changes in the fossil record. Evolution is going to happen more quickly. Just like with those that bacteria plate that you looked at, right? If there was no antibiotic present, the bacteria could just kind of go on, be in their way. But you put strong selection pressure on, like 1,000 times antibiotic, and you're going to see rapid changes. So these rapid changes known as adaptive radiation. This is a time of extreme diversification of a species. So many new species are going to evolve in a small time. And there are things that will trigger this. So if there's a mass extinction event, the flip side of that is that after that extinction, there's going to be rapid evolution and diversification, rapid speciation. A colonization event, same idea. Few organisms go to a new place. This is like the founder effect, right? And they go to a new island and it's empty. They diversify rapidly and fill all of the empty niches, right? There's nobody living in the trees. There's nobody living underground. There's nobody living, in the grass. I can diversify and fill all those spots. And then also an evolutionary innovation. So a brand new thing like wings or flowers evolves, and it's so successful that there's rapid diversification. So we're going to talk through and give a few examples of each of these. Okay, so the first one is adaptive radiation, and the most common example here you've probably all heard of is this meteor that hit the earth about 66 million years ago and killed most of the dinosaurs. Not all of them, because birds are dinosaurs, but it killed the pterosaurs. It killed the um, many marine organisms. Many plant species died. A lot of forgetting my names of all of my ancient extinct animals here, but large classes of animals went extinct during that event. Some of it due directly to the impact, some of it due to the fact that photosynthesis shut down, but some organisms survived, right? Stream communities tended to do better because they don't rely as much on photosynthesis as they do on like eating decaying foods, right? So organisms that eat decayed matter may have done better. And then suddenly they had the whole earth to themselves. Um, so there could be this rapid diversification. This includes like the age of mammals came right afterwards, right? The only mammals on earth during the time of the dinosaurs were very small, burrowing, like shrew-like mammals. But then when most of the dinosaurs died, suddenly mammals could be the carnivores, and they could be, the herbivores, and they could grow bigger, and they could take to the trees, right? Suddenly, like the whole world was open, and they filled that spot. There was selection for that, and rapid diversification. So one of the other triggers to this adaptive radiation is this colonization, right? One organism goes to a place that's empty and they can diversify. So we're looking at the Galapagos finches here. The very first finch made it over there somehow, maybe got pushed in a storm off of the South American mainland, found itself in the Galapagos, and there are no finches, right? So there's seeds, there's insects, there's fruit, there's all this stuff growing there, and nobody else is eating it. So the finch had, maybe it was a pregnant female, maybe a few finches made it over, right? They formed their own little population, and then they could divide, right? Some are going to eat the seeds, but if a few had bigger beaks and they could eat, um, like we see here, the big beak, the biggest beak here, has the crushing bill and it's eating seeds, right? Maybe some that have a slightly pointier big bill, they start eating the fruit, right? And in that population, some individuals tended to have small bills, right? And so those individuals could go off and focus on picking up insects, right? That's this guy. And there's no competition, right? So we can fill that. Other ones have a big bill, but it's also pointy, right? So they can eat cactus. So you can see how when they're given this whole world to inhabit, all the small differences in a population, everybody can go find their perfect spot, and you get this rapid diversification. And then we have evolutionary innovations, right? So a major um, physical trait evolves, like wings or flowers, and those individuals can suddenly, if you're the first flowering plant, you're bringing insects to you. You've got better fertilization than everybody else because you have insects coming, and therefore you have more seeds and you spread them further and you can kind of take over. So flowering plants were the last type of plant to evolve. So it went mosses, and then ferns, and then conifers, and then flowering plants. But they are now the most common plants on Earth. 90% of plants, when you look outside your window, including grass, shrubs, things that may have very, very small flowers that we don't notice. These are flowering plants. So it opens up a niche that wasn't accessible. Wings on insects, right? They could now get to different food sources or escape predators, right? It was so successful that it evolved rapidly to many different types of flying insects. Now, the flip side, though, to all of this rapid diversification is that sometimes there are mass extinctions, right? Mass extinction leads to speciation. So we'll talk for 1 second only, and we'll get more into this later, is this mass extinction. So this is a large scale extinction event over a short period of time. So where a large number of species go extinct at once. So there's always a small amount of extinction going on. If you look in the fossil record, things come and go all the time. And this is just due to either some competition or some small environmental changes. But when a lot of species go extinct all at once, that's a mass extinction. And so this is usually caused by some large event like a meteor or sudden climate change. That's what's going to cause a mass extinction event. And we're actually in the 6th known mass extinction event over the course of the Earth right now. So we'll pause here, and this is the end of chapter 12, and we will start up again later. Bye, everyone.